Good afternoon, everybody, and welcome to this month's IQ Academy webinar. Thank you for taking the time out to join us on our bite-sized session this month, where we'll be taking a look at cost-effective water quality monitoring with Dr. Craig Speed. If you have any questions on today's session, you can send these through on the questions panel to the right of your screen. If we don't get a chance to cover any of these, we will ensure they're addressed in the follow-up materials after the event. We'll also have a short questionnaire that will display at the end of the session today. Please take the time to complete this if you have chance, as your feedback helps us to keep the Lunch and Learn webinars relevant to your needs. Our branches are running a number of events over the coming month. Details are available on the current slide. For further information, please contact your local branch secretaries, and their contact details are available on the branches page of the IQ website. And I'll now hand you over to Craig.
Thanks, Dave. Good afternoon. Yes, my name is Craig Speed. I'm an Associate Director in the water team at Wardell, Armstrong, and I'd like to speak to you about water quality monitoring, making it high quality and cost effective. So in terms of the sort of things I'd like to cover in this session, I'd like to look at what stops water quality monitoring from being high quality and cost effective. And so potential things are monitoring design pitfalls, reduced confidence in your data through the lack of quality control checks and quality assurance samples, and failing to deliver cost effectiveness by cutting the wrong costs at the design stage. So I'd like to look at ways of getting around those things today. So first of all, in terms of introduction, there's a lot of water quality monitoring that will be delivered as part of quarrying activities by different quarrying operators. The purpose of the monitoring will be, could be a number of different things, from gathering baseline monitoring prior to doing quarrying, prior to land filling at the end of a quarry's life. They could be doing permit compliance monitoring, investigative monitoring if things need to be looked into, and perhaps as part of day-to-day operational control as well. Now, when you're setting up monitoring, it's obvious that there needs to be a balance, clear balance between the quality of the monitoring that you're delivering and the cost. So what I'd like to look at today is how to maximize the quality of that monitoring and the best ways to reduce that cost in order to optimize the cost effectiveness of what you're doing. So first of all, let's have a look at some pitfalls that can occur potentially at the monitoring design stage. So the first of two pitfalls I'd like to look at are to do with a failure to take field measurements. So sampling is not just about filling a bottle in the field with water, putting the stopper on and sending it off to the laboratory. What you need to do is you need to take field measurements of a variety of physicochemical parameters like temperature, pH, electrical conductivity, dissolved oxygen, and then for certain applications, maybe even turbidity and redox potential as well. This needs to be done with a calibrated handheld multimeter, of which there are various manufacturers that can supply these. You need to ensure that these are calibrated at regular intervals. And also, when you're taking a sample, you need to take notes about what the appearance of that sample is, whether it has any characteristic smell. These are all items of information that will be very useful when it comes to interpreting your laboratory data. Now, if you fail to take these measurements and take observations about the sample, there is a real chance that you could miss out on the full picture of the chemistry and potential pollution of a water sample. There's also the possibility that certainty that you cannot do the quality control of the laboratory data that you need to. For instance, pH and conductivity need to be very close to one another between the field measurements and the laboratory data. Also the same for turbidity and redox potential as well. So if you do undertake these measurements, if you do these sort of pH temperature measurements in the field, then it really helps you to ensure that you have a good early information on the sample and what the condition of that water sample is. That gives you some useful information about potential pollution that might be present as well. The second pitfall I'd like to talk about is loosely called the choice of sampling methodology. So again, sampling is not just filling a bottle in the field, sending it to the laboratory. There are a whole variety of different bottles that you have to fill when you take a sample. The picture over on the right-hand side actually shows what a typical sample looks like. It can be, over 10 bottles that you might have to fill with water. Each has a different purpose. For some bottles, these are for certain non-conservative parameters. And what I mean by that is parameters that are prone to undergoing changes once the sample has been taken, whilst the sample is on the way to the laboratory, or even sat within the laboratory. Such parameters could include ammonium, cyanide, sulfide, and dissolved metals. All of these things require preservatives within their own sampling bottle. And these preservatives can include small amounts of reagents that are already put inside the bottles, like sodium hydroxide, zinc cyanate, sulfuric acid, nitric acid, and hydrochloric acid, depending on which of the parameters are that you're looking at. If you're looking at dissolved metals and heavy metals, then it's also a requirement that you need to do filtration in the field so that you ensure that your dissolved metal sample is an accurate reflection of the concentration of dissolved metals within the sample bottle. Now, the reason for doing this is that there are two potential inaccuracies that can occur if you don't do these preservation and filtration of dissolved metals in the field. One is that these reactions, like chemical reactions, precipitation of the minerals, or adsorption of the metals to the inside of the bottle, can occur in transit. A second one is that there's a potential for another inaccuracy due to the order in which the acid is added at the laboratory versus the filtration, and I'll come on to that in a case study in a minute. Now, the choice of laboratory that you make indirectly determines the methodology that you put in place in the field, because the laboratory will provide you with the sampling equipment, like the filters and the bottles. So in order to ensure that you're not going to have this pitfall, you need to choose the right laboratory. At the moment, we're aware of 7 laboratories in the UK, and of the 7, 3 of those laboratories adhere to the British standard, which governs the proper preparation of samples in the field. And this is the standard that I've listed here in the slide. The other 4 do not implement this sort of correct methodology. They do not give you the field filtration and preservation equipment. And instead what they do is they are relying on the assumption that the sample will be relatively unchanged, and they can add acid at the lab and filter at the laboratory, and everything will be okay. But unfortunately, inaccuracies do occur through that route, and it can impact your data quality and the interpretation that you make once you have that data. So just to illustrate that, we had the quite sort of uncommon opportunity recently to undertake a inter-laboratory quality control, as we were helping a client to transition from one laboratory to another. So this involved taking synchronous samples from a quarry lake. We had 3 samples that were taken at the lake and sent to each of 2 laboratories. The first one, Lab 1, is a non-British standard compliant laboratory. So again, they just ask you to fill a bottle of the sample water, send it to them, and they do the rest. And the second one is a British standard compliant laboratory that provides you with the filter tips that you need, like I show on the right-hand side of the slide, and also the bottles containing the preservatives, like in the picture below that. Now, the concentrations of the results and the concentrations are shown in this plot for a number of different heavy metals. This is just a subset of the sample that I've provided for this slide. The concentrations that are being shown are in micrograms per litre on a logarithmic scale on the left-hand side. And the difference in the 2 symbols is when the symbols that are a bar, like the orange bar you see there, that just shows the level of detection. This is the minimum level that the laboratory can report. And the sort of large dots are detections that were made with the laboratory analysis. So looking at this, you can see that for barium and also for sample 1 of manganese and sample 2 of zinc, there's reasonable agreement between the two laboratories. But for aluminium, for samples 2 and 3, copper for samples 2 and 3, and manganese for samples 2 and 3, there is a fairly systematic offset between lab 1 and lab 2, with lab 1 having higher concentrations. So higher concentrations in the non-British Standard compliant lab. And this is the second effect that I went on to talk about earlier, a potential source of inaccuracy. And this is what happens when you don't have filtration in the field. The sample is likely to arrive at the laboratory, and at laboratory reception, they need to add preservatives to try to prevent any further changes to the sample. But that sample's not been filtered. So if you add preservatives to that in the form of nitric acid, then you'll tend to leach out more of the metal than was present in the sample originally from suspended solids. This causes an overestimate in the concentration of these metals, as you see here. So this is a demonstration of why it's very important to check what your field methodology is with respect to these non-conservative parameters. So let's have a look at having confidence in your data and looking at quality control and quality assurance. So having confidence in your data is essential. What we've looked at so far is some elements of monitoring design at the top of the diagram on the right-hand side. Undertaking the sampling is part of monitoring implementation that happens next. Now, once you've got the data, the thing you need to do next is review that monitoring data. It's the quality control step. Now, essentially, this is critical. Failure to do these quality control and quality assurance steps has the real risk to errors in the analysis results, consequent misinterpretation of the data, and also then the need for undertaking repeat work at cost. In order to do a proper quality control and undertake quality assurance, you really need to do a thorough review of the data after each monitoring round. You really mustn't leave it too long, because each sample, depending on the parameter, has a shelf life, a holding time. And once you exceed the holding time, which is specific to the parameter, that sample can't be used anymore. So it has to be done fairly promptly once you get the results. Also, when you're doing this review of the monitoring data, you need to have an appreciation of the potential problems, like the pitfalls, the 2 pitfalls I mentioned earlier. And also, what's really important is that you have good channels of communication open with your samplers and the laboratory that you've chosen, so that you can check any potential errors or anything you need to query. So there are 2 main types of procedure. The first is the quality control of the monitoring data. And this is really your detailed, thorough review of the field measurements and the lab data together, as I'll describe in a minute. And the second is quality assurance samples. And this can be duplicates and blanks, which I'll come on to shortly. So in terms of quality control, I've got 2 slides where I'm going to describe some of the sorts of checks that you really should go through when you are checking your monitoring data, when you first got it from the laboratory, and you want to make sense of that data and check that it is what you expect for the whole suite of data that you've got. So one of the checks, the obvious check that you make at the very beginning, is to check that you have agreement between your field and your lab physicochemical values. For example, pH and electrical conductivity. These need to be quite close to one another. The electrical conductivity, there is no reason why the EC should change in the sample from when you take the sample in the field to when you have it analysed at the laboratory. Those results need to be very close to one another. pH needs to be similar. You can expect some slight changes due to carbon dioxide outgassing from the sample at the laboratory end, and potentially in transit as well. Another thing you can check is the ionic balance of the sample. If you have a full suite of major ions, by which I mean sort of calcium, sodium, sulfate, chloride, those sorts of things, then you can check the ionic balance. Laboratories can do this for sort of £2 or £3. They can provide you with that calculation fairly automatically. and you are looking for less than a 5% imbalance between the total concentrations of anions and the total concentration of cations in your sample. And in fact, most good laboratories should be able to do that within 3% imbalance. There are some specific situations where a sample can justifiably have a different, larger imbalance, and those can include samples that don't have very much in terms of cations and anions dissolved, so low electrical conductivity samples, and very high EC samples as well. Another potential example would be if you have samples that are outside the normal pH range for waters, like very acidic samples or very alkaline samples. That would also throw your ionic balance as well. When you're looking at electrical conductivity, another check that you can make is to check what the values of the EC are against the total dissolved solids. Most groundwater will have a total dissolved solid value of between 0.55 and 0.75 times the electrical conductivity value measured in microsiemens per centimetre. Now, looking at specific chemical parameters, the first one I'd like to mention is aluminium. When you're looking at dissolved aluminium, if you get a sample back and it has a high concentration or much of a concentration of dissolved aluminium and it's a pH around 7, I would really have a look at that in a bit more detail, because aluminium is most soluble in water at high pH and very low pH. In the pH 7 area, it's not very soluble. So if you're getting high concentrations of aluminium in that kind of sample, then you want to look at the possibility that sample contamination has occurred during filtration. And again, it's something to go and speak to the lab about. Another check to make of specific chemicals is incompatible ions. So by this, what I mean is dissolved parameters that really shouldn't be in the same sample at the same time in the same conditions. So for example, nitrate in the presence of dissolved iron 2+, if you have a look over on the redox scale on the left-hand side, you can see that the stability of nitrate is isolated to the area that is oxidizing, so not just above 0 millivolts on this EH scale, but it's actually above 400 millivolts. And so it needs to be in really quite well oxygenated waters, otherwise it starts breaking down to nitrite and ammonium. Iron, on the other hand, for that to be dissolved, you need to be at the other end of the spectrum, you need to be below 0 millivolts, so it has to be reducing waters. So if you're finding both nitrate and iron dissolved in the same sample, I'd start to have a look at what else is in that sample to work out which one is wrong. Another thing that is worth looking out for and being aware of is the way that laboratories report some of their parameters. So there are some, like nitrate, nitrite, ammoniacal nitrogen, and alkalinity, that can be represented, can be reported in different ways. So just to illustrate that point, nitrate can be reported nitrate as N, it can be reported as nitrate as NO3, like you can see over on the right hand side in that screenshot. It's really important for the laboratory to be specific as to which one they're reporting, not just to say nitrate, otherwise you have to go away and check. And the reason why you need to check is because if you had a nitrate result of 20 milligrams per litre, the drinking water standard for nitrate as N is 11.3, and the drinking water standard for nitrate as NO3 is 50. So with a value of 20, you might be exceeding the drinking water standard, or you might not. So it's critical to know which of the parameters are being expressed. So it's really good to be onto the laboratory and make sure they're reporting the right parameters in the right way. Another problem that I've come across before is the way that total metals and dissolved metals get reported, and it is possible, although it's uncommon, for you to get total metal concentrations that are less than a dissolved metal concentration, and that's completely the wrong way around. And the reason for that happening that I found in the past was that during the filtration in the field, the wrong type of filters were being used, and the filter that was being used was actually leaching heavy metals into solution, so that the dissolved metal sample had more heavy metals in than the total metal sample. So that's something to look out for as well. Very basic check to make, but just check that there's less in the dissolved metal parameter than the total. And finally, the level of detection. You really need to make sure that the level of detection, in other words, the precision, the lowest reporting concentration that the lab can manage, is not above the water quality standard, whether it's an EQS or a drinking water standard. Otherwise, you simply couldn't screen against those different thresholds. So check, this is actually something you need to check when you are organising and commissioning the laboratory analysis, that the levels of precision are appropriate for the purpose. So moving on to quality assurance samples, we're still in this general area of review of the monitoring data, because when you're looking at quality assurance samples, the idea is to make an assessment of the accuracy of your monitoring when you've got the results back. So in terms of QA samples, these include duplicates and blanks. These QA samples really need to comprise about 10% of your samples if you are undertaking a number of monitoring rounds. If you're looking at a number of monitoring points, this is a best practice method to provide the regulator, in most cases, with the confidence that the data that you're presenting for whatever investigation, whatever compliance activity, that it is high quality data. For more important applications, like if it's legal or expert witness, then the percentage of QA samples really needs to be increased, perhaps double the number I've just said. So in terms of what types of quality assurance samples there are several that can be used depending on what your purpose is. I've summarized it within this table. I'm not going to go through the whole table, but I'm going to talk about 3 of these: trip blanks, field blanks, and duplicate samples. So for blank samples, the purpose of this is to check for any sample contamination that might have occurred within the sample round. In order to prepare a blank sample, you really need to be using laboratory grade deionized water. It needs to be as pure as possible. And it's best if you understand what the quality of that water is as well, if the laboratory can provide you with a certificate of its purity. Now, in terms of types, there are 2 types of blank samples. The first is the field blank. Now, what that is a sample of deionized water that the sampler has prepared at a randomly chosen sample location and then had it sent to the lab for analysis. Now, what this represents is an assurance that there's been no sample contamination during the sample preparation process, as well as in addition to the laboratory processes. The second type is a trip blank. Now, this again is a sample of deionized water, but the difference with this one is that it's prepared at the laboratory by the laboratory, and then it's sent out on the monitoring round with the bottles that are supplied. So it goes on the sampling round in the van, in the Land Rover, whatever, and then at the end of the sampling round, it's then couriered to the lab for analysis with the rest of the samples. Now, the purpose of the trip blank is again, it's a check of laboratory processes, that there's no contamination at the laboratory end, but it's also a check that there's been no contamination by volatile organic compounds during the sampling round from samples and sampling bottles adjacent to the trip blank. Now, if anything is detected, the first thing you should do is have the results checked with the laboratory for any errors at their end, like any typographic errors or any errors with the analysis, in case you need to ask the laboratory to undertake a repeat analysis of the sample. Again, that has to be done within the holding time of the sample for the parameters that you're looking at. Just a quick case study about field blanks. I was involved in an EU project in Turkey in the last 2 or 3 years, and it was a project taking groundwater samples from 100 monitoring points in central Turkey, and there were some issues that we found with contamination of field blanks. Now, The way that this appeared first of all was from my review of the data. This is an excerpt of that data purely for the polycyclic aromatic hydrocarbons. And you can see that for most of them, there was no detection of any of these compounds, except for naphthalene, which is the smallest and most volatile of the PAHs. Naphthalene was detected in many of the groundwater samples. So to look into that, and the fact that it is quite strange only having one of the PAHs present, you'd normally get some of the others present as well. So it looks strange to start with like that. But looking along the spreadsheet of the rest of the data, when you have a look at the blank results, you can see that there were detections also in the blanks for naphthalene. Now, essentially what this does is completely invalidate the samples for that parameter, for that monitoring round. So we had to get an investigation underway with the laboratory to find out why that was happening. And the possible explanations I put to the laboratory, once I found out that they were genuine values, was that naphthalene is found in industrial emissions, it's found in poorer quality urban air, and it's also a constituent of cigarette smoke as well. So I asked the laboratory, is there any potential that any of these things were present, particularly focusing on the possibility of smoke from smokers? And it turns out all the lab staff who were doing sampling were actually smokers, and although they didn't smoke during any of the monitoring, it was possible that some of the staff at the locations where they were being given access to in order to take sampling, the people who switched on the pump gear for the boreholes, that it's possible that they were smoking whilst the samples were being taken. So clearly we asked the laboratory to make sure that there was no possibility that samples were being prepared in a poor air quality environment. And after that particular check, there were no more detections of naphthalene in either the blanks or the samples. So moving on to duplicate samples. Now, what duplicates are is a check of analytical precision for the sampling round. And what this comprises is having 2 or more samples collected at the same monitoring point on the same day. Now, there are 2 different types. The first is a consecutive duplicate, and this is where you take 2 samples from the same location, the same sampling point, one after the other. So it's slightly different times. And so that's the sort of thing you can get where you just simply fill one bottle, put the stopper on it, and then fill the next bottle that comprises the duplicate, stopper that one up, and it's slightly different times for those 2 samples. So the results from this represent a combination of the precision of the analysis plus a small amount of environmental variability. Now, the second one, split duplicates, this is where you get around the environmental variability by preparing 2 duplicates from one sample, one large sample that you mix well and then decant into 2 separate bottles. So it essentially represents the sample at the same time, but as 2 parts. And so when that's sent away, that represents the precision of the laboratory only. Now, both blanks and duplicates should really be anonymized when they're being submitted to the laboratory, so the reference numbers given to them shouldn't allow them to be identified by the laboratory to make sure there's no form of bias during the analysis. Now, for duplicates, when you look at these during your quality control review, you need to have a look at calculating the relative percentage difference, which is calculated by the difference between the 2 results divided by the average result for the sample. And the RPD should be less than 10% for a duplicate sample. And again, any exceedance should be checked with the laboratory. There's an illustration on the slide there of some very low RPD results. A lot of those parameters are conservative, though. So for some of the less conservative or non-conservative parameters, the RPD percentage can go up quite a bit more, just to bear that in mind. So let's have a look at achieving sensible cost reductions with the idea of using a good monitoring strategy during the design stage of your monitoring. So just up to this point, we've been talking about the quality of your methodology, the quality of the data. So the first point to say is that by trying to ensure a high quality approach to your design, That should lead to cost effectiveness by avoiding unnecessary costs due to errors or repeat work. When you're choosing any parameter at the design stage, that choice of parameters, there needs to be a good a justification for each of the parameters you choose, whether that's for compliance or conceptual model understanding or quality control purposes. Now, how to best achieve some cost reductions and ensuring what you're doing is cost effective and optimal. There are three possibilities when you're looking at the design of your sampling. Those include the number of the monitoring points, reducing the number of parameters sampled, or the sampling frequency. Now, the first two of these, if you look at trying to achieve savings by reducing the number of monitoring points, that has the risk of reducing your understanding of the site conceptual model and the water quality of the site. If you're looking at reducing the number of parameters, that has a potential downside of narrowing down the chemical picture that you have from your data set once it's been produced. So the solution that I would suggest is, first of all, looking at a reduction in the sampling frequency that you propose during the design stage, and getting this agreed with the Environment Agency, if that's necessary, as the best way forward. So I prepared a hypothetical case study of this. What this is this case study is a baseline monitoring that's required by the Environment Agency for a hypothetical site in which monthly monitoring has to be done over 12 months. Let's assume that for each monitoring round, 5 samples will be taken, and the requirements as far as, say, the Environment Agency is concerned for this particular set of monitoring is to include pH, chloride, suspended sediments, hydrocarbons, pHs, and heavy metals. At the end of this case study, I have actually included some laboratory costs as well, which are taken from some real quotes, but please take these as indicative. So first of all, using those requirements that I outlined in the bullets a moment ago, the simplest approach to this would be simply to say all of these parameters have to be monitored every month from January to December. But you can probably appreciate that might be quite an expensive approach, but it might be the sort of thing that ends up happening because somebody puts monitoring in place without very much time to spare, in a bit of a rush, or maybe don't quite appreciate what savings can be achieved by looking at different frequencies. So the second example here is to look at using 2 different monitoring frequencies. So the top part with the field physicochemical parameters and lab physicochemical parameters, the suspended solids and the major ions would be done monthly, but the more risk-based parameters, the ones you might not find on the site on every monitoring round, you could propose those to be sampled and analysed quarterly. And provided that none of those parameters are detected above the level of detection, and provided that there are no, say, exceedances of the heavy metals, then you stick to the quarterly frequency for those. But in the third example, if you did get detections of some of these parameters, then what you'd do is you'd look to reintroduce those parameters during what would otherwise have been the monthly monitoring rounds, until those parameters drop below the level of detection again. So this is a sort of approach, risk-based approach, that is found acceptable by the Environment Agency. And if we have a look at what this means in cost terms, if you look at applying costs for each of these different parameters to those 3 examples, you can see that if you do the basic approach, just looking at, then this could cost you about £6,050 for 5 samples. If you then look at the more risk-based approach using this dual frequency strategy, then it will reduce the price to around £4,350, which is about a 28% saving on your monitoring. And in the third example, where you're having to reintroduce some parameters, as I'd sketched out previously, then you're getting a reduction of about 22%. But probably slightly more, because this example, the third example, actually assumes that you're going to have to analyse all the 5 samples for the things that were detected, not just 1 or 2. So the results This kind of approach could result in reductions of about 20 or 30% in the cost using a dual frequency monitoring strategy without losing any of the parameters from your monitoring. So these are potential efficiencies that can be savings for the company involved or could help to fund other investigations elsewhere on site. So to conclude, one of the things I've tried to outline is to try and think of the monitoring as cyclic, as I've highlighted in this diagram. We've talked about monitoring design, we talked about aspects of monitoring implementation today, and also the critical importance of undertaking that review of monitoring data. The final thing that time hasn't allowed is really where you look at your data and work out whether there are aspects of the design that need to be reviewed and changed in order to make sure the design is optimal. That is in the fourth part of the cycle. But think of it as a cyclic activity. Data quality and achieving high data quality really starts at the design stage of your monitoring. There are numerous pitfalls to designing and implementing the monitoring. I've tried to outline some of these here, but obviously it's the sort of thing that I'm very happy to help with queries on. Quality control of the data is absolutely essential. It has to be done as soon as possible once you get the data back from the laboratory. Sampling really needs to include quality assurance samples when you're looking at delivering sampling rounds and multiple samples in order to provide confidence, particularly for the regulator in the data. And cost effectiveness really starts with high quality methods to avoid the pitfalls, avoid the errors, and prevent repeat work. Finally, if you're looking to reduce costs and look at optimizing cost effectiveness, this is best achieved by looking at a dual frequency monitoring strategy. So any questions?
We've had no questions through, but if anything comes up after the event, please feel free to drop us a line at IQ or drop Craig an email just on his address on the slide there.
Thank you very much.
Thanks, Craig, and thank you for all you took the time out to join us today. As with the previous sessions, we'll be making a recording of the webinar and slides available for you all to access. We'll get an email out to you next week with those. Thanks again for joining us, and if you do have a chance, please provide your feedback of today's session on the questionnaire that will be being displayed shortly.